Good morning and good evening, everybody. Thank you for joining us for today's webinar, co-hosted by the U.S. Embassy in Seoul and the American Chamber of Commerce in Korea. Today's program will begin with remarks from our co-hosts. First, James Kim, Chairman and CEO of AMCHAM Korea, followed by Gregory Briscoe, Minister Counselor for Commercial Affairs of the U.S. Embassy in Seoul. Now I'd like to ask Chairman Kim of AMCHAM Korea to please get us started.
Hey, good morning, good evening. Thank you so much for joining today's webinar. You know, I am so grateful to Greg Briscoe and his team at the U.S. Embassy for organizing such a valuable, session today. Greg, it's really an honor to support you all the time. You know, today's event is a chance to discuss a pivotal new area of cooperation between our two countries. And it's called autonomous systems. Major companies such as Qualcomm in the US and Hyundai in Korea are pioneering what I call headline-making innovations in this very exciting field. Just yesterday, I attended a forum hosted by Megyeong, and believe it or not, it was called Beyond Gravity, and it talked about aerospace innovation. I have personally learned a lot from this forum. As today's webinar is going to demonstrate, a big number of small and medium businesses in the US are also making significant strides. Their innovations can have valuable applications in Korea as well as the United States. And today's strong turnout indicates that from the Korean government and the industry leaders that there's so much enthusiasm in both countries for more cooperation in this field. AMCHAM is ready and eager to support such a partnership. And I hope that today's webinar is going to be a meaningful step forward. And we look forward to continuing our support and collaboration with the U.S. Embassy. So thank you so much for your participation. And I also look forward to significant learning from today's webinar. Thank you.
Thank you, Chairman Kim. Now I will ask Mr. Gregory Briscoe, Minister Counselor for Commercial Affairs of the U.S. Embassy in Seoul, to deliver the welcoming remarks.
Jim, members of the American Chamber of Commerce, and distinguished guests, good morning. As noted, I am Greg Briscoe, Minister Counselor for Commercial Affairs at the U.S. Embassy here in Seoul, Korea. I'm delighted to join you today, and I echo Jim's comments about our cooperation with the AMCHAM. The AMCHAM is a key partner of ours, and we look forward and we really support this effort to provide information on the latest developments in industry here in Korea and how we can cooperate here between bilaterally with Korean and U.S. firms. I would also like to acknowledge and extend our appreciation to Iris Automation, Echodyne, and Resonon for their time and effort to share their vision and unique perspectives on the latest advancements made in autonomous systems. Autonomous systems is a highly competitive market and has attracted the recent attention of some of the largest and fastest growing companies in the world. Today's discussion is well timed, considering strong efforts in the United States and the Republic of Korea to develop, expand, and promote the deployment of autonomous systems across multiple sectors and applications. KPMG's 2020 Autonomous Vehicle Readiness Index ranked Republic of Korea at number 7 and the United States at number 4 in the world, highlighting both countries' readiness to embrace and deploy autonomous vehicles in their near future. For example, Korea seeks to commercialize Level 4 self-driving autonomous vehicles by 2027. In addition, the Republic of Korea is looking at ways to commercialize drone taxis by 2025 and autonomous flight by 2035. Korea is actively allocating resources in developing technologies and deploying autonomous systems through ground, aerial, and maritime platforms to enhance its defense capabilities. Looking ahead, as we continue to foster our strong partnership with Korea and the AMCHAM in helping Korean and American companies lead the world with innovative and cutting-edge technologies, collaboration in areas such as machine vision, perceptive sensors, both radar and laser, artificial intelligence, and object avoidance, to name a few, will be key in addressing the upcoming challenges during the transition into full autonomy. I hope that today's session becomes the stepping stone for further collaboration and partnership building. So thank you again for this opportunity and for joining this webinar. Thank you.
Thank you. Now we will hear presentations from our three companies, Iris Automation, Echodyne, and Resonon. To begin, I would like to ask Jon Damush, Chief Executive Officer of Iris Automation, to present.
Thank you very much. Let me turn on my screen share. I've got some content to share with the audience. So thank you very much for having us today. I'm excited to share with you our perspectives on a critical piece of technology that we think is integral to supporting autonomous flight specifically, but not limited only to airplanes, but other autonomous vehicles in the future. So first, a little bit about me. I'm a large fan of a fellow named Simon Sinek, who believes that if you start with why and you have a clear understanding of why you're doing something, then your organization has the best chance of succeeding and exceeding expectations. So for me, what's my why? I have a passion for aviation and the benefits that it brings to humanity. I am a commercial pilot and a flight instructor, so aviation safety is absolutely critical to me. I believe that the integration of unpiloted and piloted systems in national airspaces will not only enable economic benefit, but frankly will help elevate the global aviation system as well. We use computer vision in our solution, and I believe it offers tremendous performance at a size, weight, and cost point that is advantageous for small autonomous aircraft. And frankly, I come out of Boeing. I was with Boeing for 6 years prior to joining Iris as its CEO. I was in Boeing's future mobility division called Boeing Next. So I'm intimately familiar with the future of mobility marketplace and the technologies and the regulations involved. And I believe that there's an opportunity to bridge the gap between private funded startup companies and traditional aerospace in a way that can really advance the aerospace sector globally. So I want to give the audience a quick primer on what it takes to go fly safely. Apologize, this is very US-centric in terms of the regulations that I'm going to talk about, but jurisdictions around the world are largely very similar in that you need to certify 3 things before you're allowed to go perform a commercial operation with an aircraft. The first thing is the pilot. That involves, health requirements, vision requirements, training requirements, and then your performance requirements and limitations that allow you to go operate an aircraft commercially. That intersects with 2 other requirements and certification bases. One is the aircraft itself, which has to be certified for the type of operations you intend to do. And then the third is the operation that you're trying to do, the use case or the mission. Are you allowed to do that in certain environments, certain times a day, with certain aircraft and with certain pilots? It is the intersection of these 3 certification bases that lead to the safe aviation system that we enjoy globally today. With the advent of autonomous systems, we've effectively removed the top circle on this chart. The human is no longer in the cockpit, and we have to take care of this mutually reinforcing safety system to make sure that we still get the benefits of those reinforcements without that third circle being in the equation. So I'd like to take the audience through a really quick journey as if I was going to jump into a Cessna aircraft at John Wayne Airport in Southern California and fly to Van Nuys Airport in Southern California, a trip that's only about 50 nautical miles, so not very far. You can see by this chart, the airspace around Los Angeles is quite complicated. But that airspace is actually the first tool that helps me avoid a mid-air collision because it separates aircraft of different types, speeds, and missions. By planning a flight strategically through that airspace, I'm maximizing the chances that I have plenty of airspace around me to avoid a potential collision. Once I get in the airplane, I use radio communications to talk to air traffic control. I have a transponder-equipped airplane that responds to radar interrogations with my aircraft type and my altitude and my And I also have ADS-B that transmits my position to other participants of the ADS-B system as I fly. So I have strategic mitigations, I have tactical mitigations, and then the last link is me, the human pilot. I look out the window and I see and avoid other traffic. So the point of this chart and this explanation is that it's a set of layered mitigations that lead to safe flying. It is never one thing, it's never one technology, it's never one approach. It's these subsequent filters that incrementally remove risk that lead to a guaranteed safe outcome of a flight. So my job as the pilot is to satisfy this rule, which states that when weather conditions permit, meaning I can actually see, it is my job to see and avoid other aircraft. Note that this rule does not suggest a specific separation minimum, but instead says see and avoid, meaning don't run into another aircraft. Taken that way, it becomes clear that the human pilot in today's aviation safety system is actually the last line of defense against what we call the non-cooperative aircraft. What does that mean? It's a perfectly legal airplane. Someone's following the rules. It just so happens that in a lot of jurisdictions around the world, it's completely legal to just go get in your airplane, and given that you're in the right kind of airspace, you can just go fly without talking to anyone, without filing a flight plan, without having a transponder, and without having ADS-B. So it is the drone community's responsibility to see and avoid the human pilot in the human piloted aircraft, what we call the non-cooperative aircraft. To do that, we need to have some standards. So there's a global body called ASTM that is working on these standards very diligently to inform global regulators around how we can define the compliance requirements for autonomous systems to access national airspaces. We have two volumes of airspace, one that we call well clear, which is 2,000 feet from the drone aircraft, and another one that's 500 feet from the drone aircraft. The point of this slide is that we want to satisfy the yellow boundary, the well clear volume. The key to doing that is all about time. The sooner we can detect a target, the more time we get to make a decision to avoid and to actually execute an avoidance maneuver, which takes time. How much time? For a typical drone to move laterally 2,000 feet, it will take 24 seconds. For a typical drone to climb or descend 500 feet, it will take 30 seconds. So we're talking about being able to detect something tens of seconds in advance of a potential collision to have enough time to execute an avoidance maneuver. That's where the detection systems come into play. Our approach at IRIS is to use computer vision and artificial intelligence to detect, classify, and locate the non-cooperative potential threat target. In that left image, you can see that our system has properly detected and identified a small single-engine aircraft, and then we pass that location to an autopilot on board, which then decides to execute an avoidance maneuver. We use commercial off-the-shelf cameras and commercial off-the-shelf computers, in our case an NVIDIA GPU, and it's our algorithms that really perform the magic, that do the detection of the targets in the sky, that classify those targets as a helicopter, single-engine aircraft, twin-engined aircraft, business jet, etc. And then we can estimate the size of those aircraft from our classification, and because we know the optical geometry of our system, we can determine the range to that target, which is really the important bit of the IRIS approach. With a 2D sensor, a camera, we're able to detect how far away a target is from a single camera. We deploy that software for small aircraft currently. Today, we're deployed on a number of small drones. We can also deploy the technology on the ground to protect a large area of airspace for a lot of drone operators, or we can deploy it on larger aircraft, either alone or in conjunction with other sensing modalities like radar to provide an even better picture of the immediate area and a safer environment for the operation of autonomous systems. And then finally, I have a video to share. I'm not sure if this is going to play well, but I'll give it a chance. What you're about to see is video that was recorded from on board one of our test drones during a live test scenario. We're looking directly into the sun, and we're trying to detect an aircraft in the worst case scenario, which is a head-on encounter, where the threat aircraft is flying directly at our own aircraft. What you will notice is that our system will detect the aircraft before you can visibly detect a pixel. As soon as it detects the aircraft, a classification is made as a small plane. You will now see the box turn red. When it does, our aircraft has commenced an avoidance maneuver, which in this case is a descent, and we've avoided a collision successfully. We fly these missions every day in our flight test area in Reno, and we've flown over 15,000 encounter missions to date, recording a variety of different encounter geometries, environmental conditions, and aircraft types to train the machine learning classifiers so that we can do this generically on board any aircraft in the future. So I will leave you with this statement. We exist to enable beyond visual line of sight, unmanned aerial operations by detecting, identifying, and tracking non-cooperative aircraft. So thank you very much for the opportunity to share this with you today. I look forward to any questions. Over to you.
Thank you, John, for that presentation. Our next speaker will be Jeff Finan, VP of Business Development at Echodyne, who will talk about advancements in radar technology for unmanned systems applications.
Okay, well, it's a pleasure to be with you all this morning. As Michael stated, I'm a VP of Business Development at Echodyne, and at Echodyne, we're focused on developing kind of the next generation of radar technology that hopefully will play, an important part in enabling this autonomous age that we're entering. And I'm really pleased to be talking to this audience because we think that, South Korea, with its focus on the fourth industrial revolution, is going to help lead the way to kind of enable this vision of autonomy. And we feel that so strongly that even as a small company, the first and only international office that we've opened up is in South Korea. So I really would, and at the end, I'll have a some contact information for the person that's running our office in South Korea. And I just encourage you to reach out to us. We would love to collaborate with you and find different ways to collaborate on either airborne or ground autonomy. And then we also, our radars are used for security applications as well. Okay, so, what is this, what's a vision kind of for this autonomous world? And this is a slide that NASA came up with. And if we could kind of go forward in time several years to when Seoul is kind of a fully enabled smart city, I mean, what you're going to find is autonomous taxis that are driving up, picking up a passenger, delivering that person to a vertical takeoff and landing pad where they'll hop in an air taxi and maybe be delivered, to Incheon Airport or maybe another regional city. You'll find, packages that are being delivered for all different types of goods, like within 30 minutes or less. And then there'll be all manner of industrial uses of drones. So inspecting, pipelines or electric utilities, or helping farmers be able to get higher yields for their crops. So that's kind of the vision of this autonomous world. But in order for that vision to become a reality, these autonomous systems have to be very, very safe. I mean, the bar is not going to be how safe is a human driver or a human pilot. The bar is going to be much higher for these systems to be, accepted. And at Echodyne, we're focused on radar, but similar to what John mentioned before, we believe that it's really going to be about sensor fusion, having very capable software and very sophisticated sensors that are feeding that software very accurate information, so that the software can determine, okay, how to navigate, safely. So we definitely believe that it's going to take a variety of sensors like computer vision, LiDAR, and radar. But what I'm going to talk to you about today is radar, because obviously that's the focus of our company. So when you look at like what's a benchmark for a sensor to go after, we feel like the gold standard is the electronically scanned array radar sensor. So if you look on the nose of a fighter aircraft, that's what you'll find. And these are very, very capable sensors that can see out at great distances. They can scan a wide field of view very quickly in all weather, all environmental conditions. And so they are a fantastic sensor. So why not just take that sensor and then leverage that for self-driving cars or autonomous drones? Well, the challenge has been, and I'll use a term of art, which is called C-swap, which stands for cost, size, weight, and power. And so these are very expensive sensors, which really don't lend themselves to, high volume applications. And the size, weight, and power are higher than, what is feasible for some of the systems that we're talking about. So what has Echodyne done? What we've done is found a way to reduce that C-swap while maintaining a lot of the performance advantages of say, a phased array radar. So what you can see, on the right side of this slide being held by someone's hand is our EchoFlight radar. So, it's very small, lightweight or whatever, but it has many of the same performance advantages of a phased array radar that you'd see on a fighter aircraft. So it's a beam steering radar. So you could imagine, a pencil beam emanating from the flat panel and rapidly scanning the field of view, and then doing what's called search while track. So what that means is that we're rapidly looking through the field of view. Once we find an object, we start tracking that object, and we can go revisit it at a higher rate. So say 10 times a second. While at the same time, we're looking for a new object that might be entering the airspace, around a drone that's flying. So we have true search while track, and then have other things like sequential lobing super resolution. So what that means is that we can precisely track the object in 3D space and then be used as a cueing sensor. If you wanted to put, say, a camera to go look at that object, you'd be able to zoom a camera in, on the target. And we've developed a marketing video with some animations that kind of describes what I mean when I say, hey, we're a beam steering radar and we implement things like sequential lobing super resolution. So I'll show you that video. Hopefully it'll play okay, and it'll give you a better sense of what I'm talking about.
Its advanced features include a wide field of view, active beam steering, search while track, sequential lobing super resolution, 3D masking, and high-fidelity data output options. EchoGuard's beam steering technology continuously directs radar energy in tight conical beams across a wide field of view. The radar scans 3D space with over 2,500 unique pointing directions, each beam taking mere milliseconds to interrogate an object. When the embedded radar processor makes a detection, additional measurements confirm the exact location, size, velocity, and micro-Doppler signature. EchoGuard creates high-fidelity 3D super resolved tracks by revisiting each tracked object up to 10 times per second.
So that video is available online, and if you're interested in seeing the full version, I can direct you where to find that on YouTube. But that does a good job of kind of describing, okay, when we say we're a beam steering radar, what do we mean? And then, when we do the sequential lobing super resolution, what we're doing is bracketing the target with multiple beams to get, better position accuracy. So that's a little bit, the underpinnings of the technology and the radar. Now let's talk about, some specific examples and test programs that we've been involved with. And we'll start with the unmanned aircraft system space. And so when you look at that, in that area, you can put the sensor, similar to what Jon, talked about, you can put the sensor on the aircraft. And so that's kind of what the EchoFlight radar is about. You can put that on a drone or a small aircraft. Or if you want to set up a corridor where a drone could fly safely, you could put the sensor on the ground and then image the airspace, where that drone is flying. So those are kind of the two pivots. And now I'll give you some, some examples of different tests that we've been participated in. So, over 2019 and 2020, there's been a whole bunch of tests and programs that we've been a part of with NASA, the FAA, the U.S. Air Force, and really our work with the FAA goes back even to like 2017. And we've worked with many of the UAS test sites in the United States. And I can't go through all the different tests and programs we've been involved with, but I've brought out a few here that I thought we could talk about. So the first, we'll just talk about carrying the sensor on an aircraft. And here's a recent example of a NASA SIO test program that we've been involved with. And this was kind of a larger aircraft. And you can see in the picture here, there's two of our radars, our Echo Flight radars, mounted on each wing. And basically, they're kind of providing over 220 degrees of forward, coverage of the airspace where this UAV is flying. And then for this particular use case, what they were simulating is this UAV flying down a gas pipeline and then inspecting it. So this this test just happened in February of this year. Another test we participated in Virginia with NASA and the FAA was similar. It was linear inspection of an electric utility. So you'd have a drone flying, up and down, power lines to inspect the infrastructure. And they were flying a helicopter around, and we had our radar was mounted on a drone, and they just wanted to see, okay, how far could we image, could we detect the helicopter, and at what ranges. And so over the course of a couple of days, we had 127 tracks collected on this helicopter at about 3 kilometers of detection range. Another program that we participating in is NASA Armstrong Resilient Autonomy. So NASA has had people developing autonomous software to figure out, okay, because as I mentioned, you're going to have very capable software that is going to navigate, whether it be a ground vehicle or an air vehicle, successfully and safely. And so Resilient Autonomy is about that. They're developing that software, and then they're taking sensor feeds like from our radar to be able to learn how their software is responding. So the way this started out was, a radar on an octocopter, and then it's transitioning to a Latitude HQ-90B, which is a larger sized UAV. And you can see kind of the concept here is the radar would be behind a radome on the nose of the Latitude aircraft. Another program we've worked with the FAA is with the Assure Group, and they've been helping to support the RTCA Special Committee 228, not to get into too much of the lingo, but basically this is the standards body which is going to develop the regulations for beyond visual line of sight operations. And so Assure kind of supports the FAA and Special Committee 228. And for this particular program, they have a Tiger Shark UAV. And you can kind of see in the Echo Flight radar, their plan is to mount 2 to 3 of our radars on the nose of this aircraft. And basically, similar to what Jon was talking about, is trying to figure out, okay, what should that well clear volume look like when the regulations are finalized. And then this picture just shows some testing that has been done with the Air Force, with Air Force Research Lab. They have a program called LEAP, which stands for Long Endurance Aircraft Platform. So just imagine an autonomous aircraft that's going to be airborne for days at a time, and they want to have sensors on board that to avoid that aircraft from running into anything else that might be nearby. So we started this testing last year, and it's continuing this year as well. So that was the air portion, but as I mentioned, you can also use the sensors on the ground. And so let's just talk about a couple of examples there. This was a test that we did up in Alaska along the Trans-Alaska Pipeline. And so we strung our radars, along the pipeline with overlapping coverage. And actually, it's interesting, Jon's sensor, the Iris Automation computer vision system, was flying on the drone. So, I mean, this is an example where, you really want layered protection. Computer vision, radar, other sensors, along with the capable software to get the safety where you need it to be. So in this case, we were on the ground surveilling the airspace. The drone was taking measurements of the pipeline as well as carrying Jon's sensor on the drone to identify potential hazards as well. So that was a test in Alaska. And then another one I'll mention, which was more of an urban test. This was a test we did with NASA and the FAA down in Corpus Christi, Texas. And Corpus Christi is kind of a medium-sized town on the Gulf in Texas. And the idea here was, okay, so say you got an urban environment, and you want to set up a corridor for drones to fly within that urban environment. Let's set up a test and collect data on that. And so this had basically the corridor running from the Corpus Christi airport to downtown Corpus, and basically, trying to capture information for an urban environment, which is, more challenging than saying being out, in the middle of Alaska, where there's not a lot of potential hazards. So, that's some of the work that we've been doing with airborne autonomy, but we've also got a prototype radar we developed for autonomous ground vehicles. And so you can see it mounted on this, top of this vehicle with some other sensors. And so we're using this prototype, we're doing our own testing, and then we've got the sensor out with other partners to basically, kind of capture data and find out, okay, what is needed to truly get to level 3+ autonomy. And for this particular radar, it's got a broad field of view like our other sensors, 120 degrees in azimuth, 20 degrees in elevation, has a range of like 250 meters plus, which for this particular application is sufficient because the ground vehicles aren't moving at super high velocity. And some things that we're implementing, which we think will be important, to get to level 3+ autonomy, is something we call cognitive ready control, where basically we're going to allow that sensor fusion engine to control where they point the beam energy. So if you imagine, this software, it's got all these different sensors. It also knows the destination for the vehicle. So it knows that it's going to make a turn to the right, say in 5 seconds. Well, maybe it wants to point more radar beam energy over to the right. So we've enabled this radar so that there's a lot of adaptability, where the software can control where the radar is looking. And anyway, we'll be capturing information, from this prototype to be able to generate a production unit for industry. So anyway, that's my pitch for today. I would conclude by saying, Dominica is our the person who's heading up our Seoul office, and here's her contact information. And I would love to hear from you. So if there are areas that, you think we could collaborate, please reach out to Dominica, and we'd love to talk to you. Okay, thank you.
Thank you, Jeff. For our next speaker, we will hear from Dr. Adam Stern, who is a senior scientist at Resonon. He will discuss hyperspectral imaging for automated detection in airborne remote sensing applications.
Thank you, everybody. My name is Adam Stern, and I'm the senior scientist for a company named Resonon, and we make hyperspectral imaging solutions. And I'd like to thank also the American Chamber of Commerce in Korea, and in particular BK Instruments, which is our business partner in Korea. We've had lots of business success in Korea, and it's largely because of BK Instruments. They are an outstanding partner for Resonon, and we're proud of our relationship with them. I'm going to talk a little bit about what hyperspectral imaging is. It's a very popular emerging technology, and then I'm going to talk about its application in autonomous systems. Hyperspectral imaging is basically imaging plus spectroscopy. It's the creation of a full two-dimensional image, and at each pixel in the image, you get a complete spectra, a reflectance spectra. So as opposed to a standard camera that just gives you 3 data points, RGB, red, green, blue, like the camera in your phone, our instruments will give you images where each pixel has hundreds of spectral data points. And this is useful because different reflectance spectra, different materials have different reflectance spectra, and you can use the spectroscopy to identify different materials and plant health species and all sorts of things. For reference, note that the spectra here, this is the wavelength of light. It goes from 400 nanometers to 1000 nanometers for this particular instrument. This spectral range here, 400 nanometers to 700 nanometers, this is the visible spectral range, and then with larger wavelengths, this is off into the infrared. So these are some textbook examples of reflectance spectra. This is the visible down here from 0.4 to 0.7 and 0.4 to 0.7. And so here's a bunch of different minerals. You can see they have distinctly different spectral signatures. You can see here that plants and soil have different spectral reflectance signatures. This graph on the left is different plant species and some plant species under different health conditions. And so you can see they have different spectra. And so spectroscopy can be used to identify different plant species and even the same plant species under different health conditions. On the graph on the right shows human-made materials, which have a distinct, unique spectral signature. So even if they appear natural to the human eye, using spectroscopy, it is easy to identify them. Hyperspectral technologies is often discussed in conjunction with multispectral technologies. And so let's discuss the difference very quickly. In multispectral imaging, you just have a few, maybe 10 spectral data points, and the spectral data points are very wide, and they're often separated from each other. Whereas hyperspectral data basically gives you a continuous spectrum. So in these curves here, there's 240 data points, for example, and each data point is 2 nanometers wide. And so on the left, the graph on the left is the multispectral signal from the data on the right. And you can see that you obviously get a lot more information with a hyperspectral signal. Of course, the data files are much larger, but that's the cost you pay. So let's take this hyperspectral technology and now use it for airborne remote sensing. So let's put the sensors in airplanes or drones. And a quick history on this. Hyperspectral imaging has been around since the 1970s, but for many years, these sensors were too large for most researchers and most industries. They were only suitable for very large government and military platforms. They're expensive, they're very difficult to maintain, they're limited to, like I said, government and military applications, and often they were in satellites. But now, so look at this, very large, larger than 40 kilograms. And nowadays, there's quite a few manufacturers of hyperspectral systems, and the airborne remote sensing systems are quite small. This here is our airborne hyperspectral system, and there's quite a few on the market today that are available, as you can see in the pictures below. But this system of ours is less than 2 kilograms, and it's quite small. It's the size of a loaf of bread, and it provides very high quality geo-registered hyperspectral data, and it's designed to fit on a drone or piloted aircraft. And it autonomously grabs the data, and then the point of hyperspectral imaging is you can use it for automated detection. What has enabled this revolution in hyperspectral imaging is the fact that now you can get computers that are small and fast and cheap, and drones are available. There's lots of commercially available drones that can carry these systems. And the hyperspectral sensors themselves have become smaller and more capable and more affordable. Here's a picture of our system in a drone that we flew over a farm near our facility. And then if you fly on a drone, you can fly underneath clouds, and so you're often not limited by weather constraints like piloted aircraft. So that's quite useful. So what can we do with this hyperspectral imaging in a remote sensing package? We can use it to identify different plants. And so this is useful to identify invasive weeds in a farm, for example. So these are plants that you don't want. You can use the hyperspectral data to make estimations of your yield and to look at the crop health. You can look at nutrient deficiencies and water stress and disease. And so these are just these pictures below are just some example pictures from that farm that we took data on, and these are various analytical techniques that you can use to quickly evaluate the hyperspectral data in your scene and find out where the plants are healthy or where they need water or nutrients. And of course, you might have to go out and ground truth the area, but this will give you an automated method for detecting potential crop stress, for example. And you can actually get this data from our website. You can download this data and our software for free from our website. Here's another very popular application, an application that's popular all over the world. And that's looking at, it's a subset of ocean science, and it's looking for algae blooms, harmful algae blooms, in particular when these algae blooms get close to municipal water intakes. We have one of our customers is at NOAA, the U.S. National Oceanic and Atmospheric Administration, and they take one of our cameras and fly it on a piloted aircraft over Lake Erie in the northern part of the United States, and they do weekly flights and looking for these harmful algae blooms next to the water intakes for cities. And they make this data available to local governments. It's available to everyone, but they make a report for their local governments so that their public health experts can evaluate the water quality. In this data sets, the detection is all automated, so they are detecting the harmful algae automatically. And so to summarize, the hyperspectral imaging is potentially a very useful tool for automatically detecting all sorts of materials and plants. For plants, you can identify pipeline leaks where the leaks are affecting vegetation on the surface. We can use hyperspectral imaging to do industrial quality control and automated sorting. For example, white pills that are white to the human eye can be easily detected and differentiated using imaging spectroscopy. And other industrial applications include things like food sorting, food quality, sorting recycled materials and plastics. And then it's worth noting that hyperspectral imaging is still largely a tool that's being used for research. It's just now getting into the industrial applications, but converting hyperspectral data to useful information, those answers are not yet widely known. And so it's largely a research tool, but in a few years, 5 to 10 years, this technology will be all over the industrial landscape for automated sorting and quality control, either in factories or from airborne remote sensing platforms. So I'd like to thank you all for your time. 감사합니다. And if you have any questions, we'd be happy to take them. And thank you to our Korean partner, BK Instruments, and they are also available for any questions or comments. Thank you very much.
Thank you, Adam. We have about 10 minutes left for questions. If anybody in our audience wants to ask a question, please feel free to either use the chat function or raise your hand. In the meantime, we do have a few questions that we have collected from the audience. So first I would like to ask John from Iris Automation. For markets like the US, from a regulatory and standards perspective, what are some of the unique challenges and opportunities in the full commercialization of unmanned systems? What are some of the safety and technology thresholds that would need to be met for unmanned systems to be fully commercialized?
Well, we'll have to unpack that question a bit, Michael. That's got a lot of stuff in it, but I'll try to be succinct and brief. So I think the opportunities are pretty clear. When you start to be able to scale and democratize aviation for easier use at a lower price point, you start to really capitalize on the capabilities that a flying thing can bring your operation, whether that's for commercial gain, inspection, compliance for environmental regulations, emergency response. The opportunities are pretty clear. Some of the challenges to meet those opportunities is, I think, probably the biggest one globally that we have to worry about is public acceptance. With the advantage of lower cost aircraft that can operate autonomously and safely, that's by definition going to lead to more airplanes in the sky. And not everybody might be ready for more airplanes in the sky. So this is one of those areas that I think the industry writ large has to pay attention to and socialize properly so that we lead with knowledge and education about the benefits of unpiloted systems to help really develop a partnership with the general public when it comes to deploying these capabilities. I think the other challenge that's really significant, especially here in the United States of America, is airspace integration. We have a very dense airspace already. And on any given day, and pre-COVID and hopefully soon post-COVID, there are 44,000 commercial airliners in the sky at any given time. That's a lot of airplanes. And that doesn't include the general aviation airplanes or the low altitude helicopters. So when you start to think about adding at least that number, if not an order of magnitude more flying things to the airspace management becomes a very significant challenge. Fortunately, there's a lot of people focusing on this area. The regulator is more than well aware of the challenges in this space, and there are a lot of smart people that are focused on meeting this challenge. To the second part of your question, the safety level, it must be high. The current airline safety level is something we call, 10 to the minus ninth. And what that means is that you have a potentially significant failure, 1 in a billion operations. So that's a big number and a very, very small ratio. And you need it that way so that we enjoy the safety we have today. If you talk about expanding the number of aircraft by a factor of 10, that suggests you're probably going to need to achieve a better level of safety than 10 to the minus ninth. Now, does that mean you have to? Well, I think there's a lot of ways to achieve that. And one of the advantages of smaller, less expensive systems is the fact that you can use more commercial off-the-shelf components that are made in larger quantities, and therefore you can start to predict their failure and their reliability with a higher degree of accuracy. So probably shifts our world more towards preventative maintenance and removing systems from flight well ahead of when there's potential failure. And then finally, technology, if anything, is what's leading in this space. We have plenty of tech that goes back decades. And Korea itself has been one of the leaders in the world in terms of the development of a lot of the technology that's being used in autonomous systems today, from miniaturized compute to communications equipment to displays. The tech is there. It's really it's bringing the regulatory environment up to speed with the tech, making sure that we're not advancing industry at the sacrificing safety. And that takes some time, but thanks for the question. I hope that was a helpful answer.
Thank you, Jon. My second question is for Echodyne. So Jeff, I would like to ask you, as countries explore self-driving level 4 and above, what would be the level of accuracy needed for high-resolution satellite imagery? And are there other cost-effective means to collect imagery and data that may be used for high automation of level 4 and above?
Yeah, that's a great question. I think from our standpoint and what we've read, to really get to accurate localization where which is a critical part of enabling, say, self-driving vehicles. You need to know exactly where that vehicle is. And of course, GPS is a great technology to enable that. But when you get into urban canyons and GPS isn't available or reliable, then that's where, accurate maps become, very important. And based on the research that, we've seen in some of the projects that are out there, for example, I know Maxar Technologies has created some satellite imagery of like 25 centimeters over parts of, Tokyo and other cities in Japan. Maxar also, and there's a number of companies like Maxar. There's a company called Black Sky and Planet Labs. There's another number of companies that are commercializing satellite imagery, and the capabilities, are incredible. So, to get to 25 centimeters or lower. But Maxar also participated in a project to basically get higher resolution images from aircraft down to 8 centimeters. And then some research reports that I've seen indicated that, the localization performance at 8 centimeters was kind of well within what people thought, would be kind of the standard or the requirement to be able to accurately localize a self-driving vehicle on the road. But they went on to kind of look at, well, what about 16 centimeters and 32 centimeters? And the performance there wasn't bad either. So you're kind of, if you're in that range, based on some research that's been done, it looks like that would be sufficient. So satellites are going to be a great means to get, higher and higher image resolution. But to the second part of the question, I mean, if you just look at the comments or the conversation we had today about drones and the number of drones that'll be in the airspace, you could imagine, drones with imaging technology that could get to 8 centimeters or better, mapping out the roads in the future. So I think there's already a lot of energy based on satellite technology, but then also people thinking about how to get more accurate maps based on aircraft and drones. So it looks like, 25 centimeters is in the area where should be sufficient for localization, but there's examples down to 8 centimeters as well.
Thank you, Jeff. And now I'd like to ask a question to Adam from Resonon. Could you explain more about the applicable cases for hyperspectral imaging using artificial intelligence and avionics?
Absolutely, thank you. That's a great question. We covered it a lot before. The next step, I think, in the technology of using hyperspectral imaging is to take it out of the research field and apply it to actual industrial and commercial farms and environmental monitoring applications. So, for example, a government might contract out to planes and drones with these sensors to scan their national forests and look for health issues and other environmental concerns. And then I think one of the most popular commercial application for hyperspectral remote sensing will be in precision agriculture, in doing yield predictions, and at looking for early detection of crop stress. And it's only a few years away that these will be industrially realized applications.
Thank you. So I think we are out of time for our session today. So I want to once again thank all of our great speakers, Iris Automation, Echodyne, and Resonon, for sharing the very exciting work that they're doing. We really appreciate our co-host, the U.S. Embassy, for their leadership on this event. So I hope that all of you had a very informative and helpful session today. Thank you.